right, sir.
Control of an Inverted Pendulum by Sunil, Moeen, Natalie, Josh, and Hamad. We were tasked with making a controller that can maintain a constant position for an inverted pendulum. In order for this to be obtainable, a set of differential equations will have to be utilized to identify the transfer function that will assist in picking out the correct spring, damper, and mass combination. A larger mass makes the pendulum fall, but the spring can prevent that. However, the spring will oscillate. So to help, a damper is used to minimize the oscillation, but the damper can create steady state error. To account for this, an input motor is attached and converts current to torque to help the system achieve the goal in the desired time and specifications.
All right, modeling. The pendulum is in its upright position and can be taken as an inverted pendulum. Here, the gravity acts to destabilize position. We design a controller to keep the pendulum at a stable position. The inverted pendulum is modeled by balancing torques around the point zero. The inverted pendulum is attached with damper and a spring. They help to keep the pendulum at a stable position when disturbed. The inverted pendulum is modeled by balancing torques at mean position. Spring keeps the pendulum stable by making it oscillate around mean position, while the damping forces reduce the number of oscillations. The spring needs a higher stiffness to balance the system. Torque is provided by the motor as a control input to achieve the desired position in time with less overshoot. The torque is provided by the motor. So we obtain the required governing equations of motion that could be transformed to a controlled transfer function.
Transfer function to make a controller to the governing equation will have to be transformed to a Laplace domain, and this will create a transfer function, which as you can see it. And when we translate this to MATLAB and we made a code for this function, it gives us like a result in MATLAB, and mine will explain the result.
The equation of the overall transfer function of the system can be used to plot system's response in MATLAB. However, springs and damper has some disadvantages, such as damper made system to have a delay, and that needs attention. Natalie will explain more about it, because I feel like a controller can be used to get rid of these issues. So Natalie, you can take it from here.
We were able to get the transfer function by finding the equation of motion, and using that we used it to check the system's response by applying the step input and taking into consideration the damper and spring constants. From this, we achieved the results shown in the previous slides. The results show that the desired output is achieved with significant oscillations and overshoot as a response that is caused by springs and dampers. The next strategy can be to take a feedback of response. The feedback can be the output in real time, and the error from the desired output can be fed back into the system. By doing this, the control can be improved. A significant effect will be observed if a PID controller is applied to the system. A PID controller will minimize the overshoot and improve the overall rise time of the system.